Welcome to the next Quick Start guide. Please be aware that this tutorial follows the Quick Start frame video tutorial. Here we're going to look at portal frames, modelling quickly, wind loading and sway. The portal frame command is under the Model tab. Begin by defining the span. This then brings up a pop-up box where you can define the type of frame. Here you can also define the levels, whether it's a clear height, and also the slope angle. This is identical to the Tekla Portal Frame Designer input for new frames. Once complete, we can also adjust the haunches, add parapets, ties, and so on. We'll be using a basic frame for this. Another video will cover the options in more detail. For long span portal frames, I recommend exporting to Portal Frame Designer as this goes to plastic design. Tekla Structural Designer will cover elastic design. More importantly though, Tekla Structural Designer allows 3D models, which we will now convert ours to. 3D effects may be significant when we add in wind, which is where the full model can help. We'll create a frame view on grid line C to add in some Eaves Beams. If we open this view, we can add in the top Eaves Beam, ensuring that we select the correct characteristic in the properties. We'll be copying this to the opposite side. This means that we are using the structure's symmetry to our advantage. I'm going to cheat and add in a bottom row so I can use the infills command under the Edit tab. This allows me to define a number or spacing of members within a bay. I can then window over the bays, select the direction and complete the command. Even with the temporary bottom row, this is quicker than individual modelling. If we remove the dummy bottom row and copy it to the opposite side, use the copy window to deselect any members you don't want repeated. This allows you to be clumsy with the windowing and refine later. I recommend removing construction lines unless specifically required. Right-click on one of the portal frames to open the corresponding frame view. We can use this view to add in our gable posts. Here I'm using the construction lines. These are better suited to a sloped or elevation view. We're going to be using these as a reference to insert our gable posts. Be conscious of which is end one, as this carries the support when inserting these posts. Before copying these, we will also run a validation check. This confirms whether there are any modelling errors. We can see that we have a warning for our member intersection of our gable posts. This is because steel members are typically split where they intersect to allow for connections. Where we have a member which it is not, it alerts us. We can ignore this knowing that it is correct. Next, let's begin adding in our purlins. If we start by adding in the roof panels used for wind loading, we can use the view they create to more easily add in our purlins. We'll start with the beam which runs through the apexes. We will be mirroring the purlins over, so only want the apex beam once. Similar to when we were defining the Eaves Beams, this is created as a bay. We can now use the Create Infills command to insert the purlins. The characteristic option in the properties is important to assign. This has some member-related defaults such as end releases. It also assists in controlling the checks which are performed during the design. Cold rolled members are not designed in Tekla Structural Designer. However, as these will be assisting in the analysis and the restraint of the frame, I want them to be considered during this process. Select your purlins and mirror them over to the other side. I prefer using the plane command. We can select this in the properties window. This allows me to define a plane using 2 points rather than just one. Again, as with the copy command, ensure only the members you want are selected in the window to avoid duplicates and erroneous members. Next, we can apply some dead and imposed loading onto the roof panels. Although designed for wind, they are simply a decomposition tool. This method is identical to the member loads that we looked at previously. To move forwards with wind loading, we need to add in our wind panels. The key to these are to make them as large as possible, one per plane, excluding inset stories and parapets. These panels are again a decomposition tool only. We're going to be loading them using the Wind Wizard and the brief data which is included. The Wind Wizard is located underneath the Load tab. Use the direction and overlaid compass to align the wind to your structure. We'll be using the map by eye, however a reference is more accurate. Where orientation known is unticked, the worst case will be taken in each face. The brief data only covers the UK. For other regions, you can input your own data. All the wind data is editable, however it's pulled from brief, so it's relatively accurate. If you have site-specific data, make any edits as you go through. This is true for all dialog boxes in the Wind Wizard. In the results, we get 4 primary directions. These will be interpolated between. This means that the worst case in that range, for example positive to negative 45 degrees, will be used and applied for direction 0. You can hit details to interrogate the calculations behind the scenes. Next, we go to the wind load cases and hit auto. This automatically generates all the wind load cases based on the code you have selected. Last step before looking at what's been applied to our structure is to take both of the roof panels and set the roof type in the properties to be duo pitch. This ensures they are correctly zoned based on wind direction. We are now using the wind view and related tabs to investigate what's been applied. In the top left, switch the direction we are looking into. The loading bar will only allow relevant directional load cases to be selected. Check the zones, pressures, applied loads and such. You can also edit these. Notice that the wind direction moves anti-clockwise. We will run the combinations generator and create our lateral combinations. We first select the tables to consider and the additional options, for example, accidental load cases. Next is our strength combinations, followed by service. Again, all these numbers are still editable where you wish to make changes. The default values are taken straight from the selected code and load cases which are available. We then come to match up the wind directions and EHF loading. Direction 1 positive matches with wind direction 0. As the wind direction moves anti-clockwise, direction 2 positive then matches with wind direction 90, and so on. Loading working perpendicular or against each other will not be the worst case scenario and so will be ignored. Before we run a design, we'll run an analysis on a few combinations. This is to check our structure is stable and that we have no excessive deflections. The results show us that due to having pinned supports and no bracing, our model is falling over. It is ultimately the engineer's decision how they want to address this. I'm just going to show you a few different options. We need to address this prior to running a design so that we get some reasonable section sizes through. Excessive deflections may also stop a higher order analysis or design from running at all. We'll reduce these deflections using the review view. One of the most useful views is the fixed/pinned view. Click on a member to cycle between fixed, pinned or a moment connection, or double click on a member to individually select its releases. We'll also add some stiffness to our supports. Window over the model and then use the properties drop down to isolate the supports and add some rotational stiffness. As you can see, we're using a spring linear stiffness to do this. If we now rerun the analysis, we can see how those deflections have been changed. The deflections are still quite high, so we'll add in some more stiffness. In the status window, we can see that the analysis has run successfully. And if we go back to the review view, fixed pin view, we'll add in some moment frames. By default, steel columns and concrete members will be fully fixed. All steel beams will be pinned. Click on the end to toggle one side or the centre to toggle the entire member. Cantilevers are created under the Show Alter State view. We'll now rerun the design to see whether we've made enough changes. Using the key on the left-hand side, we can see that some of the members still need work. Moving to the results view, we can use this view to show why some of the members are failing. The buckling of the central portals suggests that we don't have enough restraints and require additional bracing in the structure. This is backed up by the warning in the sway check. Again, it's the engineer's decision as to how to fix this problem. These are just some suggestions. In Review View, Tabular Data, we can look at the sway checks in more detail. This table shows us the breakdown of the calculations. We can see that the AVCRIT is between 4 and 14 for direction 1, but less than 2 for direction 2, which means that we need to stiffen the structure rather than advancing to a second order or sway-sensitive analysis type for our design. How you'd like to address this issue is completely up to the engineer. Here I'm demonstrating adding in some bracing. However, you could do this using additional moment frames, adjusting the spring stiffness or otherwise. Thank you for watching.